Hey folks, today we're talking about limits at infinity. So last time we talked about what a limit is, a couple of times ago, last two lessons, we've talked about what a limit is. And today we're specifically looking at limits as we head off to infinity. So today we're taking the limit of a function at infinity. Now to figure this out, usually we take something that's really complicated and we try to turn it into something that is going to have the same end behavior that is much less complicated. And that's what we call the end behavior. Well, I think I misspoke there. So we're trying to find the limit of a function at infinity, which is also known as the end behavior of the graph. So if you remember, we did this in pre-calc when we looked at quadratics, any polynomials, right? X to the third, X to the fourth, X to the fifth. And we looked at what their graphs were doing at the end behavior graph. So the notation that we're talking about would be the limit of f of x as x approaches infinity, or the limit of f of x as x approaches negative infinity. So the way we want to think about this is we're going to take a function that is very complicated, and we're going to try to turn it into a function that has the same end behavior, but is much less complicated. So this equation is really complicated. There's lots of ups and downs in the middle, but I know at the ends, this graph essentially looks like a 3x to the fifth. And the reason that occurs is because this term gets so massive, so much faster than these terms. Now this is, you can think about this in terms of millions of dollars. If you have $1 million times itself 5 times, you're having a huge number. That number is so big that even taking 1 million and timesing it by itself 3 times or 2 times or once is, I don't know if that made sense. But my point is that these are getting bigger. This is getting so much bigger, so much faster that these start to fall away. So you can kind of, when it comes to analyzing limits as you approach to infinity, you can kind of ignore everything except what we call the leading term. Now, 99% of the time, the leading term will be the first term, but you do have to be a little bit careful. Sometimes the leading term, they don't have it in what's called standard form, and so you wouldn't have the leading term as the first term. You might have to search a little bit. So just do a quick double check to make sure that the term with the highest degree is the first term. So the way I think about this is there's 2 ways to think about it. One way is to think about making a quick little sketch. So what is the sketch of x to the fifth? Well, let's start to plug in really, really positive numbers. So what's a positive 5 times? So a positive to the fifth is a positive times another positive is still positive. So this end of the graph is going to be going upwards. Let's take a negative now. Any negative number, a negative number to the fifth will still be negative. A negative 5 times, negative times a negative times a negative times a negative times a negative would still be negative, and then we're timesing it by 3, positive, which would still keep it negative. So that's the end behavior of this graph. Now, what's happening in the middle? I don't know. This thing could be going up and down a bunch of times. I mean, it can only cross the x-axis a maximum of 5 times, but I don't know what the ups and downs, the mins and maxes are. But I do know that the end behavior is going to look like this. So then I could now say that the limit as x approaches infinity of 3x to the fifth. I'm already regretting that I'm writing this all out. I could have just written down the answer, but I'm stuck with it now. And then I forget a plus 11. Disaster. Equals. All right, so as x goes towards infinity, that's what this is saying. As x goes towards infinity, my graph goes up towards positive infinity. So you can either write infinity or positive infinity. So that's option 1. Option 2 is, and I like this one, now you still have to eliminate, you only have to look at the leading term, but what's cool about this is you can also just direct substitute infinity into the problem. What's infinity to the fifth? Infinity. What's infinity times 3? Still infinity. Positive infinity. Now, there's some tricks and things we have to be a little bit careful of when you do this direct substitution of infinity, because infinity is not a number. It's kind of an idea or a location that you're headed to on the in the coordinate plane. But that's kind of a nice way to think about one way that you can evaluate the end behavior of a function. So let's try that with this one. Again, I don't care about these terms when it comes to the end behavior, when it comes to the limit as we approach the infinities. So now the limit as x approaches negative infinity, that's the same as if I plugged in negative infinity. What's negative infinity to the fifth? And this is what I'm talking about, how to clean something like this up. The way I've been writing it, I've been saying negative infinity to the fifth. A negative to the fifth is still negative. So what I do is I bump out the negative like that, and then I think through it. Infinity to the fifth is infinity times a -3 would be negative infinity. Now, according to Corpy, you can also call these DNE, which I'm not so sure about, but I'll trust him. He says that you could also write DNE for these. I'm not so sure about that, because even though I guess infinity isn't an actual number and maybe an answer to a limit should be a number, I think that you could answer. I feel like these are one-sided limits, and one-sided limits to me always have a solution. But he said that you could also write DNE there. I'm going to encourage you not to do that and to actually write the infinities. All right, well, now we've got kind of the basic idea of all polynomials. So now you could do any polynomial from here on out. You would make either a sketch or you'd plug in the infinities. Now let's look at what happens when you don't have a polynomial. So I'm going to encourage you to pause here, or I'll give you 10 seconds. I would like you to tell me what kind of a shift this, I would like you to identify the parent function, and then I'd like you to tell me what kind of a transformation. I said shift, but I meant transformation. What kind of transformation does this have? Go. All right, let's see how you did. Okay, so the family is e to the x, and then the transformation, okay, so this is something that's attached to x. So instantly, I know it's going to be horizontal. And then what does a negative multiplied to a function do? It reflects. It always reflects. So this is a horizontal reflection of the parent function e to the x. So we should be able to make a decent sketch here. I'll encourage you to pause again. With a dashed line, I'd like you to sketch what e to the x looks like. All right, e to the x is any one of our exponential growth functions, so it looks something like that. But we want to transform that function with a horizontal reflection, so then that would look like, I would reflect it horizontally. So now I'm going to draw this in a solid color, and it looked like this. Okay, let's now analyze this. So I'm taking the limit of this solid graph as x goes towards infinity, and it looks like it levels off at 0. Now, let's say if you're somebody who wants to figure out how to do this by plugging in, doing a direct substitution of infinity, we would get something that looked like this, e to the negative infinity. So this is where your algebra skills come in. What does e to a negative mean? It means I have to flip it. So this would be 1 over e to the infinity. And if you take e, which is like 2.718 blah, 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 and you raise it to bigger and bigger and bigger powers, what is this going to end up heading off towards? Infinity. And that's the same thing that we could look at with the, remember the dashed line is the original e to the x graph. So as x goes towards infinity, e to the x goes off towards infinity. And then what's 1? If you took one pizza and you divided it by everybody on the planet, essentially how much pizza would you get? You would essentially get 0. So a couple of things to point out there. An infinity on the bottom is the same as a 0. 1 over infinity is 0. So actually, let's make a little note of that. I think this is worth making a note. Note. 1 over 0 is infinity, and then therefore 1 over infinity is 0. So the reciprocal of 0 is infinity. Sorry, let me say that again. The reciprocal of 0 is infinity, and the reciprocal of infinity is 0. Now, this is the first time that we can talk about when your graph levels off, when your end behavior levels off at a number, we could talk about these things called HAs. You might remember that from pre-calc or even from what we've studied already this year. That means that the graph ends up leveling off at y equals 0. And we'll talk more about, actually, let's just jump down here and do this right now. So, here's a little definition. My lights turn off. If the limit of f of x as x approaches infinity is L, or the limit as x approaches negative infinity is some number L, then we can say that f has a horizontal asymptote at that value. So why didn't we say that for the first two examples? Well, they didn't level off at a number. They leveled off at the infinities. So this isn't a horizontal asymptote. This, because I leveled off at 0, is a horizontal asymptote. All right, let's see if you can do part D. So pause here and see if you can do it on your own. Okay, let's see how you did. The limit of e to the negative x, well, we already have a graph of that. That's the solid one right here. Now x is approaching negative infinity, so that's going to launch upward. So I'm going to say it's going to be infinity. Let's just double check this by plugging in a chugging. So this would be e to the negative of negative infinity. What's a negative times a negative? That's a positive. So that would be the same as e to the infinity. E, any positive number, let me try again. Any number greater than 1 raised to infinity is going to end up being infinity. So we end up at the same place. So do we have an HA here? We do not. No, we do not. All right, the limit of sine of x. Now this gets a little bit tricky because when I plug in infinity, I can't really evaluate sine of infinity. So let's do this by looking at the graph. So I'm going to encourage you to make a little sketch here. Pause and sketch sine of x. Anytime I sketch a trig function, I'm going to go with 4 tick marks, and then I'm going to rotate around the unit circle. So this is 1, 0. This is 0, 1. This is negative 1, 0. This is 0, negative 1. I'm going to start to do this less and less throughout this year. I expect you guys to be able to do this on your own without me showing you every time, but I'll show you one more time. So we're doing the sine graph. Sine is the y value. So my y value starts at 0, goes up to 1, goes down to 0, goes down to negative 1, goes up to 1. Let me try that again. Goes up to 1, goes down to 0, goes down to negative 1, goes up to 0, goes up to 1, goes down to 0, So as we go off to infinity, what happens to my graph? Well, as sine of infinity, and I don't know if this is mathematically correct, but sine of infinity is going to just bounce between these values between negative 1 and 1. So sine of infinity is just going to keep bouncing back and forth between negative 1 and 1. So we don't level off at a number. And if we don't level off at a number, we can then say that that limit does not exist. Okay, now these next two, these are one of those that fall into that category. And I say that a lot this year, that these are things that are I would say, beyond what I would expect for this class. But if you never see problems like this, then you'll never start to remember problems like this. So eventually you might have to take a class that would expect you to know how to sketch these. And those AP test takers, those of you who want to get a 4 or a 5, the College Board expects you to be able to sketch these. So I want to show you real quick. It's not as scary as it looks. Real quick, how to sketch these. So what you want to do is you want to sketch all the possible values of x and negative x. Now, I don't have a great way to explain why it's x. Well, I guess I do. Because I'm not going to get into it. I'd have to really think about it, and I'm not prepared to really think about it. So you're going to have to just get the showing you how to do it, not why it works. So what I'm going to do is I'm going to sketch the graph of x. So there's the line y equals x. I'm also going to sketch the line negative x. And that's the part that I was talking about that I'm not sure how I would explain. Why you also have to do negative x. And then what happens is the sine graph then gets caught between these values of x. So as I sketch sine, where did sine start again? Sine started at 0. So as I sketch sine, it's going to get continually caught as it goes around, and it's going to get bigger and bigger and bigger, and then it's going to do the same thing the other way. One of my favorite functions is this function. I think it's a very cool function. If you type it into your calculator, it's really cool to look at the graph. I'm not going to do it for you, but you could check it out if you wanted to. Anyway, now that we know this, what's the limit? As you go further and further out to infinity, does this graph level off at anything? No, it bounces farther and farther up and down. So this would definitely be a does not exist. This limit does not exist. So let's have you try to do a sketch of what 1 over x times sine x looks like. So using the same idea that we did here, see if you can sketch it. I'm going to give you a pause or encourage you to pause. Okay, let's see how you did. So the first thing I want to do is I want to sketch the boundaries of 1 over x. So 1 over x, that's our reciprocal family, is going to look like this. And then I also want to sketch its reflection. What would be a good color here? I guess yellow. I don't like to use yellow when I use blue because then it looks like Michigan colors. Let's use brown. Then the negative of this would look like this. Okay, and then I would sketch the sine graph in between. So now this is really crazy because the sine graph is then going to bounce. So sine starts at 0. But then it's undefined here, so it's like an asymptote. And you get these massive values that kind of go like this. And then this one is like this, swoosh, 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 bounce, 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 bounce. And then we can look at and step back and say, okay, what happens as you approach infinity? Does this graph get closer and closer to these values that are bouncing back and forth start to level off at a number? And this time the answer is yes. These do start to level off, and they start to level off at the number 0. And that kind of looks like that's the answer right there. So does this graph have an HA? Yes, it has an HA. It has an HA because our graph levels off at a number, at a value. We get an HA of 0. So those two are kind of tricky ones. I wouldn't expect you to be able to do those. Definitely wouldn't expect you to be able to do those on your own. But I also think that the more you see them, the more likely you are to start to remember them. So a couple of things to point out about HAs. VAs are discontinuities. HAs, horizontal asymptotes, are not, he repeats, are not discontinuities. HAs just tell us what the y values of the graph approaches. I don't think that that's probably a correct sentence, but the HAs just tell us what the y values of the graph approach. All right, so here's another one of these functions that if you're an AP test taker, if you're one of the people that are going to try to go for a 3, a 4, or a 5, you would want to be able to sketch this graph from memory. So I'm going to show it to you once because I wouldn't expect you to be able to sketch it yet. So we have to talk about it before you can do it. So let's sketch first. This is going to be arctangent squared. So arctangent squared is going to be hold on a second. So I'm going to change this problem. I don't want it to be squared. I mean, we could do it with the squared. It would just take the arctangent graph and bump all the negatives up. but I want to look at it from the perspective of just sketching arctangent. So let's go here and change this, delete the squared. So I want to just sketch the end behavior of arctangent. So to do that, I want to sketch a graph of arctangent. Anytime I do trig, I'm going to go 4 tick marks. And anytime I do trig with the reciprocals, or sorry, the inverse functions, or reciprocal functions, because I'm trying to sketch tangent right now. This is going to be a sketch of y equals tangent of x. And then we're going to use the graph of tangent of x to sketch the graph of arctangent of x by turning it into its inverse. Anytime I want to sketch the reciprocal trigs, I usually kind of go in both directions so that I can see both sides of my graph. So let's start off. If I want to graph any of my trig functions, I'm going to use my unit circle to guide me, just like we did with sine. So this is 1, 0. This is 0, 1. This is -1, 0. And this is 0, -1. So yet again, this is not something I would expect you to be able to do. That's why I'm not encouraging you to pause here. But I am encouraging you to see this and then be able to think through it again on your own later on. So let's see if you can, actually, I think I am going to have you pause here. Let's see if you can decide what's happening at each one of these tick marks, knowing what you know, that tangent is sine over cosine or y over x. All right, let's see how you did. So tangent, sine over cosine, which is the equivalent of saying y over x. So at 0 radians, which is right here, I would say 0 over 1, 0 over 1 is 0. Then I rotate around to 90, pi over 2, 1 over 0, y over x. 1 over 0 is undefined, and on a graph, undefined means an asymptote. Then I do 0 over -1, which is also 0, and then we do -1 over 0, which is undefined, and then you might remember this from last year, that now I can just keep going 0, asymptote, 0, asymptote, and so on. Now I need to start to sketch one of the branches, and the way I remember this is this from 0 to 90 is the same as quadrant 1. So whatever's happening to tangent there is what's going to be happening to my y values here. So if I take any value in here, any radian or degree in there, and I do y divided by x, it's going to be a positive y and a positive x. So tangent is positive in quadrant 1, which means the graph is going to be positive in that section as well. And then from there, I just remember what tangent looks like. And I remember that tangent is a periodic function, so I just start sketching all the other branches of my tangent graph. All right, now this isn't the graph that we want, though. We want to sketch the graph of arctangent. So what I could do is I could define arctangent at any gap. I can pick any gap that I want to be my definition of arctangent, but mostly we pick the gap that makes the most sense. And the gap that makes the most sense is my first kind of full cycle of tangent. So what x values does this go from? Thinking about how we count around the unit circle, I'm going to give you 10 seconds, 5 seconds, figure out what those x values are right there. Okay, so hopefully you caught on that this is pi over 2, or 90, right? That took us up there, was our first tick mark. That was 90. This is -90. So those are my x values. So if I'm looking at an inverse, they become my y values. That's the whole idea of an inverse, is that you can flip back and forth your x and y's. So this is going to be the line y equals pi over 2. And this is going to be the line y equals -pi over 2. And then now let's sketch what happens to our function, and we're going to sketch that and then inverse the graph. So as x gets closer to pi over 2, my values are positive in that direction. So my graph then, instead of going positive towards x over 2 this way, I'm saying x over 2 instead of pi over 2. As x gets closer to pi over 2, what happens to my values? They get closer and closer to the asymptote. So as I go forward here, my values are going to get closer and closer to pi over 2. And then that's the exact reverse in that direction. So now we have a sketch of y equals, this is the graph of y equals tangent inverse of x. Now they used arctangent in the problem. Arctangent, tangent inverse, they mean exactly the same thing. So now we have a sketch, which means now we can start to analyze the limits. So we want to analyze the n behaviors. Notice, underline that S, n behaviors. That means we have to find both of them. So the limit of f of x as x approaches infinity. The limit of f of x as x approaches negative infinity. So as x goes towards the positive, my graph is leveling off at what y value? Pi over 2. As x goes towards the negatives, my graph is leveling off at negative pi over 2. It also asks us to find the equation of any horizontal asymptotes. Well, we look from our theorem here that whatever, if your n behavior actually levels off at a number, those automatically become horizontal asymptotes. So we have two HAs. We have an HA at y equals pi over 2, and we have an HA at y equals negative pi over 2. So I'm just going to combine them into one equation, y equals plus or minus. That's actually two equations there, but it saves me a little bit of writing. What do you think? What do you think? That makes sense? Okay, I think we're going to keep going. I'm going to muscle through this page, and then I probably will pause there and do the next one in another video. So, evaluate the end behavior of the following rational functions. So a couple of things to remember here. We're going to ignore everything except the leading terms. So this becomes 3x squared over 5x cubed. Now notice it's not equal to that. That's why I write these arrows, because they just behave the same way. If I asked you to clean this up, you would say that there would be a 3 on the top and a 5x on the bottom, because you can kill off two of those x's. And then what I would do here is I would plug in my infinities now. So this would become 3 over 5 times infinity. Or 3 over 5 times negative infinity. Well, if I do 5 times infinity, I get infinity. So 3 over infinity or 3 over negative infinity. But we talked about this on the other page. If you divide by, I left a note here, infinity is on the bottom. Now, I don't care if it's positive infinity or negative infinity. If you divide by these massive, massive numbers, your graph is going to level off at 0. So then now I can go ahead and organize this into a statement. My limit of f of x as x approaches infinity is 0. And my limit of f of x as x approaches negative infinity is 0. To evaluate the end behavior. So it doesn't say we have to write HAs, but do we have any HAs? Yeah, we have a HA of y equals 0. All right, let's use that logic here and try to analyze this problem. So I'm going to first kind of break it up into, who does this graph act like? This graph acts like 3x to the 5th over 5x to the 5th. If I said clean this up, what would you get? I would get 3 over 5. Game over. So I can now identify my limit of f of x as x approaches infinity. If I plug infinity into this, where there's nowhere to plug it in, and I would just get 3/5. The limit of f of x as x approaches negative infinity is also 3/5. Now, the last case, things get kind of tricky here. Things get a little bit tricky. You have to think about this in terms of once we clean it up. So this would behave like 4x to the third over negative 2x squared. Which, when I clean it up, would end up being negative 2x. All right, now let's do our infinities things. Let's plug in our infinities and see what we get out of this. So if I plug infinity into this, I would have negative 2 times infinity, or negative 2 times negative infinity. So then that end behavior would look like the limit of f of x as x approaches infinity equals, well, what's negative 2 times infinity? That would be negative infinity. Then I would have, I think I'm running out of room here, the limit of f of x as x approaches negative infinity. So what did we get when we plugged in negative infinity? Well, negative 2 times a negative, and negative times a negative is a positive, and leaves us at positive infinity. So plugging in the infinities is actually kind of a nice little trick. It's a nice little trick. So if you remember, just a quick review of last year, you might remember this when we did rational functions. What's the characteristics? Why did this graph have a limit of 0? Why did this have a graph or a limit of 3/5? Why did this have a limit of infinities or DNE? Well, it's where the x's are, and it's how many you have and where. In this case, I had more x's on the bottom, which means the bottom got bigger and bigger and bigger, and when you divide by infinity, you actually get 0. In this case, it was a tie. I had as many x's, x to the fifth, as I had in the numerator as I had in the denominator. So x to the fifth over x to the fifth is going to cancel. So as we get bigger and bigger on the top, we get bigger and bigger on the bottom. The bigness cancels out, and it's always at a ratio of 3 to 5. So then I have these values, this limit value of 3/5. And then over here, we would talk about the top gets bigger. So now infinity gets bigger and bigger and bigger. Well, infinity divided by 1, let's say if we clean this up, right? Infinity divided by 1 would go off to infinity. So these first two have HAs. They leveled off at a number. So if I went back to this, I would say this has an HA of y equals 0. Here, we could say this has an HA of y equals 3/5. Well, what happens here? Does this have a HA? No, it doesn't have an HA, but it does have this thing called an SA, a slant asymptote. So anytime that the numerator is bigger than the denominator, to try to figure out its end behavior model, you would have to do a little bit of work. So let's talk about that. I'm going to highlight a couple things. The first thing I want to highlight, example 3C above did not have an HA, but it did have another type of end behavior asymptote called a slant asymptote. And how do you know whenever you have to check for slant asymptotes? If the degree of the numerator is greater than the degree of the denominator, then the end behavior model, try to highlight that a little better. The end behavior model will be a polynomial whose degree is the difference of the degrees of the numerator and denominator. So what I mean by that, or what Corpy, I should say, means by that, is up here, what's 3 take away 2 is 1, x to the first. These two things are going to behave similarly. Now, what's tricky about this is not the slant asymptote. Let me show you what I mean. I wish it were. Trust me, it'd be a lot nicer. So alpha f1, numerator, denominator, 4x to the third minus 2x squared, plus 4x, subtract 7, over negative 2x squared plus 5x minus 9. Okay, so I'm going to graph that function first. Does this behave the way that we thought it would? As x goes towards infinity, my graph is going down to negative infinity. As x goes towards negative infinity, my graph is going up to infinity. Let's type in now the graph of negative 2x. And let's see if that's the slant asymptote. Clearly it's not. Do you see how this is not leveling off at that curve? So what we have to do now is we have to figure out what is the equation for that curve that this graph levels off at. And if you remember from last year, the way we do that is by doing some long division. So I'm going to take this function, I'm going to divide it out. Now, why couldn't we do long division here? Well, it'd be over. It'd be over. As soon as you divide it, it'd be x to the fifth and x to the fifth. This is an x to the second, which can't be divided by an x to the third. So you don't have to worry about it on these two, which makes sense because they already leveled off at a number. But in this case, so they took the same problem and put it down here. In this case, I can do some long division. I can clean this up. So I'm going to encourage you to pause here and see if you can remember how to do long division of polynomials. Okay, so the negative 2x squared plus 5x minus 9 is doing the dividing into 4x cubed. Oh, don't forget to check 3, 2, 1, none. Okay, we got them all. Negative 2x squared plus 4x minus 7. So I didn't have to add any zeros in there. Then I take the first thing and I divide it by the first thing. So that would be 4x cubed divided by negative 2x squared. That would clean up to be negative 2x. So that negative 2x then goes here. And then I multiply. Remember, you got to distribute here. So negative 2x times negative times a negative is a positive. X times x squared is x cubed. Negative 2 times 5 is negative 10. X times x is x squared. Negative 2 times x, negative times a negative is a positive. 2 times that's 18 with an x. What's the saying? Draw the line. Switch the signs. So that's gone. Negative 2 plus 10 is 8x squared. 4 take away 18 is negative 14x's. And then the negative 7 drops. Repeat. So now I'm taking 8x squared. And I'm dividing it by negative 2x squared. The x squareds would cancel out. Negative 8, or 8 divided by negative 2 would be negative 4. So now I can put a negative 4 here. And if you've done this enough, you know that the game's over at this point, but let's just go ahead and explain why that happens. I don't think you're probably to the point where you can just look and do this. Negative 4 times negative 2 would be 8x squared. Negative 4 times 5 would be negative 20x. Negative 4 times negative 9 would be positive 36. What's the saying? Draw the line, switch the signs. So that's 0, that's 6x, and that's negative 42. And then now, because this degree is higher than this degree, we cannot divide any further. So now we would try to rewrite this thing as negative 2x subtract 4 plus, and remember we take the remainder and we put it over the divisor. So that would be 6x subtract 42 over negative 2x squared plus 5x minus 9. All right, now if that was a long division problem, that would be the answer, or what you'd write right there. But what we're doing is we're taking this thing and we're looking at this function as x approaches infinity. And as x approaches infinity for this term, who's getting bigger faster, the numerator or the denominator? The denominator is. So this term, this thing, goes to 0 as x approaches positive or negative infinity. So what happens is that term drops away, and then if that term drops away, what I'm left with is what my graph levels off at, which is called the slant asymptote, or the SA. Now I'm going to prove it to you that that is the slant asymptote by coming back to our calculator. I'm going to change this from negative 2x to negative 2x subtract 4. And now what will happen is this line, negative 2x subtract 4, will fit right along that graph. It'll be the asymptote. So here's the original graph. And then here comes the slant asymptote. See how it fits in there just perfect? how it lays along. Where now I'm going to zoom out a little bit. Negative 50 to 50. Let's go by fives. Negative 50 to 50. This might be too big. Let's see. Here's the original graph. You're going to have to really look for that little bump. You can barely see it. And then here comes the new graph. Yeah, 50 was too big. Let me try 20s. Negative 20 and 2. Negative 20 and 2. Let's see if this looks better. I want to be able to see that little bump in there. There it is. Okay, yeah, this will work out. Here comes the other one. Look at it's going to be so close, asymptotic, and then it shows that in the middle it's not asymptotic, but at the ends it is, which is what we're talking about when we're talking about an end behavior model. Okay, so I think I'm going to pause there. I don't know if I should talk more about the end behavior model. The end behavior model is just, if I go back up above, like the end behavior model is this. The end behavior model is what we use to analyze what this graph is doing at its ends. So don't get too caught up in what that means. You do need to remember that if our limits level off at a number, that's our HA. If it doesn't level off, if it goes to the infinities as we go to infinity, then you got to go find a slant asymptote. All right. Good luck. Try some of